So in today's video we're going to talk about electrochemistry or electrolytic cells, and these are different than the cells we've been studying up to this point, which are voltaic cells. Voltaic cells have negative free energy. They're able to run spontaneously. These cells that we are going to study actually have positive free energy. And so one way to look at those is they are spontaneous reactions run in reverse. They will not spontaneously run. So within this, we're going to kind of study these 5 points. And the way to jump in will just kind of get you back to what you're familiar with. We're going to study voltaic cells just real quick, just to review. Keep in mind in a voltaic cell, if you have an E cell that's positive, that would mean that it should run in the forward direction. So we are going to talk today about electrolytic cells, which would run in reverse direction. So in this cell that we're studying, you have iron that undergoes oxidation, and you can see that by looking at the reduction potential for it is more negative than the tin-2 reduction potential. So therefore, the tin-2 is going to undergo reduction, and iron-0 is going to undergo oxidation. So if you look at the electrode on this half cell, iron's actually going to undergo oxidation. Iron 0 goes to iron 2 plus. And in order for that to happen, it creates 2 electrons. That makes that particular electrode negative. That is the anode. The iron 2 plus would then dissolve in solution. You would have to have some help from the salt bridge to counterbalance the charge, so chloride ions would come over from the salt bridge. And again, remember that the negative anions always move to the anode. And then on the other side, on the positive or cathodic side, that would draw electrons towards it to the positive side. Those electrons would be transferred onto the cations in solution, turning tin-2 plus into tin-0, which would actually not occur out in the solution. It would actually happen at the interface of these electrodes and literally plate the electrode. You'd have to replace the cations that were removed with cations from the salt bridge. And of course, a reminder again, at the anode, oxidation occurs. So therefore, you would literally be chewing up the metal if it was an active electrode. And at the cathode, reduction occurs, which would be creating more metal, so the cathode would be growing. Now, comparison-wise, we're going to take that exact same electrolytic cell and we're going to run it in reverse. So in order for that to happen, it won't happen spontaneously. If I connect that circuit up there, I'm still going to be, nothing's going to happen because we've already shown that we've consumed the free energy. So now what we're going to do is we're going to actually get a battery or a power source and connect it to that. And in this case, the E cell would actually be negative if you did the calculation the way we're going to do it. But in order for this reaction to run, if the E cell in the forward direction is about 0.3 volts, we're actually able to run it in reverse by literally changing the poles of the battery. Okay? So let's just pay attention. One way to keep track of this, it feels like the cells get shifted in the battery, but a better way to kind of keep track of it is always remember anode is always associated with oxidation and ox, and cathode is always associated with reduction, a red cat, and that won't change whether it's voltaic or electrolytic. It's just the charge or the poles that are on the cell. And the way to keep track of that is to remember in the electrolytic cell, this isn't naturally creating charge. You have to force the charge in order to force the event that you want to occur. So for example, the anode is oxidation. So in order to strip electrons off of something, which is oxidation, you would need a positive area to rip the electrons off. So in this case, tin could lose 2 electrons to the positive pole of the battery, so it would make it tin-2, SN2 plus. And those 2 electrons could be transferred into the battery. And that tin-2 plus cation would then go into solution. Of course, then you'd have to get rid of some of the cations that have been transferred from the salt bridge. So this is all running in reverse. On the other side, you're trying to force reduction, and in that case I would need electrons from the power source, so the negative charge, i.e. the electrons from the battery, would force that reduction. So they would be forced onto the iron 2+ ions, making them iron 0. And that would actually happen at the interface of the electrode. I've drawn it in solution, but it really is the solution where that contacts the interface. Salt bridge would run in reverse. There's no need to have that extra charge in the solution. And again, one of the keys, whether it's electrolytic cell or voltaic cell, there's always got to be charge balance. And in order for this to happen, the voltage would be greater than 0.30 volts. Now again, there's a temptation to, because we're running it in reverse, to switch the signs, but literally as you're doing it, what you do is you get the voltage from the source, whether it's a battery or an external power source, and you just switch the poles. In other words, you rewire it such that the poles are appropriate, but the amount of voltage is still this greater than 0.30 volts. So a lot of times with batteries, the charges can be a little confusing, but I would tend to think about if it's negative, there's electrons associated. If there's positive, then it's a lack of electrons. And once again, the naming is the same here. If there's reduction occurring, you call it the cathode. If the reduction is occurring, then you're going to start to build that electrode back up. So then that loss of material would start to build up. Certainly not as neat and nice as the same shape. I just did that for this diagram. But the mass would start coming back. On the other side, you have the anode, which is oxidation. So that means that the tin that had built up earlier in spontaneous mode, now that you're driving it with the battery, would start to go away because of oxidation. And so that material would then go away, and you could get back to your close to your original state. I'm sure the electrodes wouldn't be quite as pretty. And when we get to the battery section, we'll study how you can do rechargeable batteries in such a way that you don't keep messing with the surface area, because the electrode goes away and then it comes back, and it would be willy-nilly how that started to regrow. So the keys to the electrolytic cell are: one, it's non-spontaneous. You need an external power source, whether that be an outside battery or a socket or an outside power source of some sort. Again, oxidation takes place at the anode, as it did in the voltaic cell. Reduction takes place at the cathode. The difference is oxidation is driven by a positive connection from the power source, while reduction is driven by a negative connection from the power source. This can be confusing. I kind of try and frame it this way. You have to think about this being driven from outside sources. And if I wanted to drive oxidation, I'd have to strip electrons. So bringing a positive charge nearby would rip electrons off of something. If I needed to force electrons onto something in reduction, I would need to bring those electrons nearby. So a negative connection from the power source certainly brings electrons near. So I don't want to just talk about electrolytic cells unless you understand why we use them. Of course, as I just pointed out, you can recharge your batteries. So that is the key to all of these rechargeable batteries we have on our cell phones and our laptops. It's used for metal plating. When you look at a lot of features, maybe they're the door handles you have in your house or apartment, or cabinet handles, they're all nicely metal plated. Or even if you look around the sink faucets in the room, they're metal plated. Chrome features on a vehicle, that sort of thing. Electroremediation, there's ways that we can use outside power sources to force charged ions out of, say, like water or dirt, in order to, if those particular ions are considered to be biohazards of some sort. Metal mining and refining, some of our pure metals that we have, and here's a list that are commonly done by electrolytic means, are refined in the mine by actually electrolysis. And finally, there are some things you can learn by applying electric current to unknown solutions to identify concentration and identity of anions or cations in water or in solid state. So let's start with the recharging batteries, and I've just got a couple pictures here that are probably familiar to you, where you have power tools or you have a cell phone that has a rechargeable battery. The keys to the sustainability of this particular activity, which you've seen in your lifetime, is how they've improved, is kind of what I'm driving at. One of the keys is extending the time that batteries deliver current, and I think the most important or relevant application of that is for electric cars, which, as I've put these slides together, this good-looking BMW e-car has a range of 114 miles, and obviously if you guys develop, or girls develop, more technology that will allow batteries to have a longer lifetime, that will further the length of an electric car. Safety is important. As we know from the Boeing Dreamliner battery problems, that this actually started a plane on fire. We can always improve this. If we can improve the safety along with the performance, that's going to help things get to the market better. Robust materials, along the same notes with safety, just a reminder about the Galaxy Note 7. Really just a poorly designed battery that didn't have much robustness to it, is almost put an end to that particular launch of a new cell phone that was pretty highly anticipated. But the last thing I'm going to just mention, which is unique, and I'm going to show you a small video about that, is I just want you to understand that an electric engine itself is a very high performance engine. It has been from the design, can develop lots of torque, has a lot of performance, as this next video will exhibit for you. So another application is metal plating. So as I said, a lot of the things you can see, features in the room, etc., can be plated. These are for small items that are metal plated. You attach them actually to connections and then drop them into plating baths. And we do that like with car hubs and bumpers and just a lot of faucets in the features in the house. Alternatively, if you're trying to get a bigger item electroplated, you could attach leads to the item itself and spray the charged ions onto there, and they could actually electroplate on the spot. It's kind of electro deposition. But we do have older techniques, and as I understand it, the Colorado State Capitol was redone. The gold plating was done in this way, where you actually have a primer that interacts with a gold material as it touches the surface. There's a redox reaction that sets that in place. So I want you to understand the general design of a plating cell, just as you did from the understanding the general design of batteries. One of the key features is that of course, there's an outside energy source, and I just wanted you to be familiar with this notation in electrical diagramming, where you have the alternating small then large line, and you have multiple ones of these. These represent batteries in electrical diagrams, and actually for every small large combination that represents a single cell. So this might be 2 cells in series, and usually the negative end is associated with the small slash and the positive end with the large slash. And so here we have a plating cell where, let's just say, we're putting copper onto this little heart pendant down here. So in this particular case, the solution is a copper 2 solution that you're dipping it in. So I have to get copper 2 to copper 0. That's what the plating is. And in order for that to happen, I have to force that. So I want to put the negative lead from the battery onto the target, is what I'll call this. And it is reduction it's undergoing, so that still gets the name cathode. And on the other side, this is the anode. And if you'll think about a plating bath, we want to avoid the use of the salt bridge. So one way you can do it is if you have a backside anode that actually is the material you're plating, it will continuously be replenishing the plating bath. So this copper will be oxidized into copper 2 plus and replenish the bath as the copper 2 plus is then continuously plated on. And so this is a traditional plating bath, whether it be copper or nickel or chromium, whatever you're using to plate your target. Now on the other side, there's electroremediation, and here's an example of that where you've actually set up as you study this, you'll notice it really has a lot of the components of a battery, where you have the anode, you have the cathode. The only difference again is this is driven by an outside energy source. The unique thing here is that the solid ground itself can actually become the salt bridge, so that if you had a cation or an anion that was undesirable in the dirt, like say you had a heavy metal problem, you had chromium deposition, or you had high copper levels or something that might be dangerous to the environment at high levels, you could actually set up this electroremediation port, and the metal ions would move in their appropriate direction to replenish the salt bath. So this is really like a salt bridge. And then you could basically get on the other side and keep flushing this. Either let the cations come out and deposit on the electrodes, or you could actually just, this shows a kind of a treatment system where you're actually purging this water as it builds up salts. And you could also imagine the same thing with anions. Say you have a nitrate or a cyanide, something that would be toxic in the dirt. You could move it out over here to the anode side. It's very interesting. Same variation. Let's just say that you have an inner salt bridge with only a salt pourable membrane here, and you could literally load salt water inside here, and it could act as a salt bridge to drive whatever reactions you want. This particular example from the literature is actually doing this acetate to carbon dioxide reduction, while as the water is oxidizing to O2. This other electrode, but once again, in order to do charge balance, then the salts are moving as if they're a salt bridge, and that desalinates the water. So that's an interesting system. So in these reactions, the electrolysis cell drives the movement of contaminant cations or anions, acting like a salt bridge into half cells. Contaminants then can either be actively oxidized or reduced onto the electrodes, or they could just be removed by flushing that half cell. But once again, I'm just going to show you my generic design, and once I didn't change a thing just so it would simplify things. So this would show you the remediation of a metal bath, for example, if you had metal ions floating in water. Let's just say you have copper 2 plus contamination. It would make the water kind of a deep blue, as you see in a lot of decorative fountains and that sort of thing. But that actually is a dangerous situation for aquatic life, and that's what they do, is purposely poison it with copper, and it kills many of the living organisms in there. But if that happened naturally, that would be actually a waste site. So we'd want to get that copper out of the water, the copper ions out of the water. the way that could happen is you could set up the same thing as your plating bath, but here's the problem. We don't want to continuously replenish the copper 2+ ions, right? What we want to do is we want to put an electrode in there, an anode in there that doesn't put a dangerous metal in there. So you could use a less toxic metal, something that's commonly used, but that's kind of a hard trick to pull off. So a lot of times what you do is you use an inactive electrode like carbon or platinum that won't contribute ions. And so now you could actually hook up a power source. And I'm going to put the half reduction table here so you understand a few things. We're going to learn a few little tricks out of this. So we're going to take a little power source, we're going to wire it up, and I'm going to start off by helping you understand, well, where do you start this electrolysis? What's the voltage we choose? And we go back to your half reduction tables, and you can see that copper 2+ will go to copper at about 0.34 volts. So that is your starting point. But we've learned that you actually have to run a little higher voltage, and that's called overpotential. So overpotential is the additional potential that's required to overcome just entropy effects, and it also overcomes sometimes there's inefficient electrical conduction, so you have to have a little higher voltage to get through that, especially anytime you change states. So for example, in this particular example, we have a solid carbon electrode going to a liquid bath or waste solution, and the waste solution then is plating onto another solid copper electrode. So all those interchanges are inefficient in conducting electricity or charge, so we have to give them a little extra voltage to overcome that. So, and you usually see this in heat loss. All right, so in this case now, we have a solution set up, and keep in mind again, this is my original diagram, but now we're talking about getting copper 2+ out of the water. And in order for that to happen, we don't want to be replenishing from this electrode, so we put an inactive carbon electrode. Now you can imagine though, as the reduction takes place, there's going to be less and less copper 2+, but the chloride ions stay behind, so we're going to have this unacceptable buildup of negative charge. Free energy would take over and the cell would shut down. Again, reminding you that if you want to drive oxidation, you should do it with a negative charge. So we hook up the proper negative lead to the lead that we want to force reduction. We dial in a little overpotential voltage. If we see that it's 0.34 volts, then this will happen. If you give it extra overpotential, and away you go, you start plating this copper 2+ ion, which is the target we're trying to get rid of. It would land on this copper electrode. The copper electrode would start to build up, and at some point you could pull that out, and that would actually be refined copper, which you could resell to recoup some of your costs. But as this occurs, the chloride ion is going to build up, so you have to offset that voltage build up. So you would actually have to keep increasing the voltage the entire time that you're running the cell to keep up with the fact that the chloride negative ions would be building up to overcome the entropy that's going on here. Now I just want to point out a couple other points along here, and one of those is right here at 1.23 volts. So remember that this is occurring on the oxidation side, so we run this in reverse, and you can see at 1.23 volts, water could literally run in oxidation mode and create oxygen gas and some acidic protons and release 4 electrons. So if you keep building up the voltage enough, you'll finally get over to an overpotential above this oxidation potential, and you'll actually start oxidizing the water, and it will turn into oxygen gas. You'll see bubbling at the electrode, and if you put a pH stick or pH probe in the water, you would see it actually starting to become acidic. So at that point you would actually have to, from time to time, do some other sort of chemistry on it to neutralize the water. But we've talked about that in the last section. You could do that with a weak base, carbonate for example. And I would also point out that if you got the potential high enough, which you are not, because as long as this keeps going, you're going to still have water present to keep oxidizing. But you do have to be conscious of these situations because chloride is not that far away from that. So you could actually literally take chloride ions and turn them into chlorine gas, which is actually poisonous. Of course, that would be evident. It'd start to smell like a swimming pool around there. Part of the take home from this is that you understand that as you pass these thresholds, these other reactions can start going into effect is if you have the voltage high enough. And so that's the one caution with overpotential. Have your half reaction table on hand so that you don't start in on another species. And I give you this advice that if you ever want to think about, well, what are my potential species that could start undergoing oxidation, will go into your target area and just look at all the possible species. So in here we only had water, chloride -1 ions, and copper 2+ ions. And as long as none of those species are in the target zone, then you're not going to start accidentally oxidizing those. Okay, I mentioned metal mining and refining. I just, I'm kind of stuck on copper here, but I would point out that in the copper mining process, there's multiple physical extractions, precipitations, even some thermochemical processes that you end up with these, they call them copper anodes, and they're blocks of copper that's about 99% pure, which you would at first glance say, well, that's great, but that's not quite pure enough to run copper wires and many of the copper, metal ware that we use in cooking and that sort of thing. So there's one more step that will actually bring that to completion, and that is those copper anions are dropped in a copper sulfate plating bath. You just run that reaction and then basically transfer that, as we showed you earlier, in the plating bath, and you come out with 99.9% pure copper. So long story short, many of the metals, some of them are made purely that way to make them, especially when you need to get them to a certain high purity. The last step is done with electrolysis. And then last but not least, I did mention analysis. This is where if you had an unknown, say metal or an anion in solution, could you identify it with electrochemical means? This is a potentiostat setup, and I'm not going to go into all the pieces, but I just kind of want to give you a glance at that. This is a common electrical potentiostat in the lab. You can kind of make out these cells in here where you actually are able to put in, jars of sample and then expose them to control current conditions. And I'm going to show you just a common experiment where you basically you start your potentiostat at in this case, a high voltage, and you start moving in this direction, which is becoming, now look at the bottom curve, and you can see in terms of voltage, it's dropping voltage. Now keep in mind, negative and positive are kind of meaningless in this work, as they are in most potentiostat work, because what we set up our reduction tables, the ones you have studied, are relative to the hydrogen couple. These potentials here are actually relative to silver plus couple. In other words, silver plus 1 to silver is considered 0, so the whole table gets shifted over. But the point is, when you want to read something like a cyclic voltammogram, what you want to do is look at the direction you're going. Are you increasing or decreasing voltage? And in this case, I'm decreasing, so I'm moving towards the negative area, right? So moving towards negativity means I'm forcing electrons onto things. And as I do this with the sample, nothing happens until you get to a certain point, right? And then there's an event, and that's right here. If I'm moving into the negative region and I force an event, that would be reduction, because I'm forcing an electron onto something. Okay? And so the event that happened here is that, say I had a metal that was 2+ and it turned into a metal +1, or it turned into a metal 0, possibly. If you can do the forward reaction, you can do the reverse reaction. So the reason this is called cyclic voltammetry is you tend to run all the way down to the end of the cathodic event, and then you change direction and you start becoming more positive, and then you force the oxidation event on your way back by, And usually this is considered to be a reversible reaction because you can just run this through the cycle over and over again and you get the same peaks. And the location of the peak is involved with the species that did the, in this case, the reduction. That is an identifier. The voltage at which this takes place is an identifier of what the species is. So that's kind of a qualitative event. The quantitative event is the size of the peak. So the more material that is in the solution, the higher this particular peak height will be. And that is the current released in the oxidation or reduction event in this case is indicative of the concentration of the analyte in solution. So you can get two pieces of information, the identity based on voltage and how much is present based on this peak height. And if you wanted, you'd set up calibration samples, and basically as you increase the concentration, you get higher and higher peaks, and you correlate that with the exact concentration. This is a very sensitive method. I'll show you that here in a second. And once again, I just remind you that at the end of these cyclic voltammetry scans, you tend to cycle back the other direction and see if the event is repeatable. And so just to give you a feel for how accurate these are, I'm just going to show you, basically we do a cyclic voltammetry scan. The electroactive species in here is the copper center. Now this is encased in a carbon skeleton, and you can see that there's these phenyl rings here, and each one of those has double bonds in it. And now just the slightest little change, we just attach one ring on the very top, so it's proximal to this copper, but it's no longer all the double bonds in the ring like it is at the top. And with that little change, look how much the potential shifts. So the way that the copper oxidizes or reduces is still the same, and then you reverse it and you get it to oxidize back, and this is reversible. But by that simple change in structure, you actually have moved the voltage considerably, because if you look at this top scan, it's happening at about 0.80 volts, somewhere between 0.80 and 0.97 is kind of how you read these. And then this guy is between 0.69 and 0.89, so it's shifted over almost 0.20 volts, totally based on structural changes. So I just show you this to kind of indicate how particular these guys are based on not just the metal or the electroactive center, but also their particular structural environment, which is very cool. Small changes in structure change voltage at which reduction and oxidation take place. Again, I point out the smallest change in structure and how it's changed the peak pattern position in terms of voltage. I don't expect you to be able to perform cyclic voltammetry, but I do kind of want you to generically understand the analysis. Some skills I would like you to be able to do are basically outlined right here in this simple objective. Could you calculate the amount of metal deposited in a unit of time with a given amount of current? All right, so this is for the electro refining in terms of mining, or electroremediation if you're trying to pull metals out of water. It's the same thing for electroplating. It's kind of the same calculations. So one of the keys to doing these kinds of problems was discovered by Michael Faraday. So there's a picture of Michael Faraday. He defined Faraday's constant at 9.65 times 10 to the 4 coulombs of charge in every moles of electrons. So I just want to remind you again, coulombs is what we, in electricity world, we use as a standard amount of charge in a set number of electrons. There's that many coulombs in a mole of electrons, so that helps us understand that. And then current itself is how many of these coulombs flow by every second. So in 1 amp is 1 coulomb per second. So here I have this nice picture of Faraday, and just for demonstration's sake, this is not true, but I'm saying that that's a water bottle there beside him. All right, the rest of the problem, though, and this is very seldom outlined in a textbook exactly this way, but I really like to put this in an equation form that, look, you can find the moles of metal deposited by taking current times time, dividing it by N, and Faraday's constant, and we'll talk about all these particular parameters of the equation here in a second. I call this the Edith-Elsner equation, or simply the EE equation, and that's based on one of my former students who actually electroplated her water bottle with her own name. And so she took her stainless steel water bottle in our CCD labs and electroplated her name on there in copper for one of our little lab projects, which was kind of a kick. Within the equation, moles is the moles of metal that can be turned, by the way, easily converted to grams via molar mass. You know your stoichiometry. Current, I would recommend that you enter that in terms of coulombs per second. If you're given amps, always turn amps to coulombs per second. Time, if it's going to all work out in terms of units, you're going to want that in seconds. N is the moles of electrons per event. N is the electrons that are shown in the half reaction table. For example, if I have a copper 2+ reduction to copper 0, that's a 2 electron event. And F is Faraday's constant, and coulombs per mole of electron, which we now know is 9.65 times 10 to the 4 coulombs, and that's something you should definitely commit to memory. So here's an example. How much copper in grams could Edith deposit on her water bottle from a copper sulfate solution if she applied 0.25 amps of current to her electrolysis apparatus for 30 minutes? So kind of the keys here is you got to have the mass you're looking for, you got to know current, you got to know what kind of solution it is, and this is critical that you know whether if it's a metal, it's what's the charge on the metal and what state are you moving it to. We're taking copper 2, moving it to copper 0, so that's a 2 electron event. And then last but not least, you got to know the time frame. In this case, it's 30 minutes. So we're going to take our EE equation, as we call it, and we're going to plug and chug. So the moles of metal deposited, we're going to take current at 0.25 again. Always convert that to coulombs per second. Don't leave it in amps. We are given 30 minutes, so we plug that in for time. Of course, you can always resolve your time issues on the fly. This is all a multiplication equation, division equation, so it's okay to put a conversion in there as long as it's a conversion that involves multiplication and division. In this case, there's 60 seconds in a minute. I divide by the number of moles, which is 2. And again, I remind you that it's a lot more efficient to put that on, just flip the equation, and then you can leave the whole equation in 2 lines. And then I'm going to divide by Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electron. And last but not least, the question doesn't ask about moles, it actually asks about grams. So I'm actually going to put that conversion at the end of this reaction because that also is a multiplication equation. So with all this in place, I can actually figure out the moles of metal deposited, which actually I'm trying to figure out the grams of metal deposited, right? And I start doing my dimensional analysis, see if my dimensions worked out, cancel coulombs, cancel seconds, cancel minutes, cancel moles of copper, cancel the moles of electrons, and I'm left with grams of copper, which is my target I'm looking for. And when I do multiply everything on the top and divide everything by the bottom, I get 0.15 grams of copper. Now, just look at this equation. Again, I want to remind you that, look, we solved for this, basically, and converted it to grams. But you could solve for the current you need. You could solve for the time you want to run this reaction. You could solve for, is it a 1 or 2 or 3 electron event? And obviously, Faraday's constant is the same every time it's constant. So you could solve for current, time, or for n, the number of electrons. Just for example, is it an iron 3 to 0 couple or an iron 2 to 0 couple? You could solve for that if you had enough information. What I'd like for you to do is get your paper and pencil out, stop the video, try and work these problems on your own. When you get done, restart the video and check your work. So problem 1, again, we're going to just basically set up the EE equation. We're going to plug and chug, trying to get to 1.50 grams of cobalt. We're solving for current, so that's unknown. We got 2 hours. We're going to go ahead and convert on the fly, and in this case, there's 60 seconds per minute, 60 minutes per hour, so those together are 3,600. Sometimes you might want to put 2 lines of conversion in there. That's fine. Now it's cobalt 3, and you're electroplating the metal, so you're going through 3 electron transfer. Of course, then you put in the molar mass, which is 58.93 grams of cobalt per mole of cobalt. You plug and chug, do your algebra to solve for current in this case, which is right here. When you solve, you end up with 1.02 coulombs per second, or 1.02 amps. Number 2, same sort of setup. You basically set up your equation. The nice thing is you're asking for moles of silver that you're plating. You plug and chug. You're solving for time in this case, so you just leave it in the equation unsolved. Don't have to put the molar mass in. You can solve for time, and the units will just fall out. When you're done, you plug and chug, solve algebraically, and you'll have 618 seconds, which if you want, you can convert to minutes or hours if that's helpful to you. Okay, for the last problem, you want to get out your half reduction tables immediately, and I even as I'm looking at this, I realize that that's probably a poorly written question, because you're probably not going to want to use silver chloride as a plating bath because it's insoluble. Although it'd be interesting to run, because you would have some solubility, and as you drive the reaction electrochemically, Le Chatelier's principle would take in, and you keep replacing the silver as you go. But I'm sure that you do need a lot of over voltage to make this happen, which is a side note. But for practice purpose, let's just pretend that the silver goes into solution so we can just kind of run through this problem. The lower end of the voltage would be above 0.180 or 0.80 volts. This is where silver plus the silver 1 couple is. You have to go above that to have overpotential. The upper end of the voltage would have to stop at 1.36 volts, because you don't want to start turning chloride ions into chlorine gas. But once again, it's kind of a poorly written question, because you probably wouldn't want to use silver chloride. You probably want to use something like silver sulfate, or actually you want to use something like silver nitrate that would be soluble. It's good practice though, and to think about how you would hook it up. The oxidation would be a silver bar, because you are able to keep replenishing the solution as you go along. In that case, the lead would be positive to force oxidation. The target is Faraday's water bottle, would be attached to the cathode. That would be where reduction takes place, and silver ions are reduced to pure silver. In that case, the negative lead would be attached to force reduction to occur. So I hope this whole little conversation has helped you understand the non-spontaneous electrochemical deposition part of electrochemistry.